Um, Thanks for being here to learn about the real-time analytics ecosystem at PayPal. Today, we are going to cover the use cases, architecture, and our technology choices for enabling real-time at PayPal. We are from the analytics platform team, and we will cover this topic. And before I get started, everyone knows the power of data, like how powerful data is, right? And proper and timely insights into the data can be really powerful. It can give you really good actionable insights. It can add to the company's bottom line, and it can be a customer delighter. So let's get started. So I am Sanjeev Koranga. I am an engineering manager on instrumentation and analytics team at PayPal. I am working on making behavioral analytics fully self-serve in PayPal, and also responsible for creating all the tracking clients, libraries, and SDKs, which enable the data on the edge to move to all the backend, right? And I built one real-time analytics pipeline, which I will be discussing today.
Hi, I'm Shobna. I manage the tracking platform team that collects all the behavioral and the server-side data. I work out of the Bangalore office in India.
Okay, so the agenda today is basically first we are going to cover on a higher level which use cases the tracking platform team is covering in PayPal. And then we will go over the tracking platform architecture, like what are our technology choices which are making things happen in PayPal, and then what challenges we faced during building our pipeline, and what solutions we came up with to solve those problems. And then we'll show you the overall architecture, like overall diagram, like which different open source components we are using to make this happen. And towards the end, we will do one deep dive on a real-time use case class, which we will cover. So let me first talk about the data and analytics at PayPal, right? So I bet many of you here have used PayPal in the past, and are you using PayPal in one form or another? You might be using it for shopping online, or basically sending money to your friends and family. PayPal is more than just a button on the shopping sites. It provides now a range of financial services and products to enable transacting money on both online and offline, easy and simple, right? And then for the scale of data, we have many different PayPal companies, PayPal, Venmo, Zoom, Braintree, Paydiant, and we basically collect all this data in our analytics platform. Just to give you some perspective, last year, 267 million users collectively transacted worth $578 billion of TPV. And that translated into our analytics system as 250 million decisions, 25 billion computations, and 60 billion queries into our analytics platform. With this, Shobna.
Yeah. Before I get started on what the tracking platform does and everything, let me start with a real-time example of mine, so it becomes easier for everybody to relate to. So at times, when I start late from office, I get a notification, say from Zomato, to order food online. And it comes with an offer as well. By the time I take the cab and I reach home, I get another offer from Uber Eats that says, order dinner today, you'll get tomorrow's dinner free. So it's even more tempting now. So how does all of this happen? It's because, I'm being tracked real time, and I've already been, there are intelligent machine learning models that have been built that has categorized me to be lazy, though comfortable for me. So when my mother-in-law goes, she's lazy, all that I can say is, don't blame me. Blame the models that have already been trained to categorize me as lazy. So it's exactly the same thing that we do for PayPal. So there are two things that went behind this. One is models that are trained by data collected over time, and the other one is the real-time data that's collected and it's also enriched with details like the geo, device, customer details, intent details, and so on. So now moving on to the use cases. So anything that you do with PayPal, say whether you do any transaction, whether you reach out to a customer support agent, create a billing agreement, add a bank, or anything for that matter, all of the data is actually tracked by us. We collect close to 18 to 20 billion events on a daily basis, and that helps solve the product managers on any of the feature that they are building to interact and provide an enriched customer experience. Say for any feature that is released in PayPal is first experimented. So when a new experiment is actually launched, the product manager of that feature would want to know real time on how that experiment is behaving. That helps them decide if they have to ramp up, down, or keep the experiment going as is. The other thing is, it also helps us detect any anomalies in the system and create alerts. These are all the various different aspects in which the same thing that I just said with an experiment also applies. Now that you know what we do and why we do it, let's move on to how we do it. The volume and the variety of data that we collect is actually growing on, it is increasing on by time. To handle this, the platform needs to have some basic capabilities. Some of those capabilities we expect or we use the framework, and some of them we build as an application on top of that framework. Here are some of the capabilities that we expect from the framework. It needs to be scalable, resilient, message-driven, fault-tolerant, and low latency. From the application, we collect data from the web, mobile apps, and from all the mid-tier services of PayPal. We also support our tenants. We collect data from our tenants like Venmo, Zoom. We also have merchant integration as third-party integration, so we can help them get insights. We do real-time enrichment, like what I just said, which is the geo detail enrichment, device, customer, intent, and all of those. So the downstream systems who want to use it can use it for any purpose of theirs. We also do some real-time normalization. Governance, which is being talked about heavily now, we started collecting data from everybody. It needs to be normalized to an extent before the downstream applications can use it even real time. Obviously, because data is also being collected real time and being sent for the downstream applications, legal compliance is something that needs to be built all the way throughout the pipeline. Moving on to the architecture. The first part is acquiring the data. So we said the data is from multiple different sources. So how is the acquisition layer built? The biggest challenge with the acquisition layer is unmanageable growth in data that we are getting. So we have our tracking service. It gets data from the web flows, mobile flows, merchant integrations, tenants, and so on. So we say the service gets about 100 requests per second. And we are able to process only 70, and the service processes only about 75 requests per second. We are losing about 25 requests per second. 25 requests per second. This leads to 90,000 requests per second either being lost if it's on full, if the back pressure is applied full end to end, or it leads to a degradation of the application in case we start to store them inside the service. So the acquisition service is expected to be responsive, scalable, resilient, and message driven. Basically, it should give a positive experience under any situation to every user request that we receive. And how do we achieve this? We do it through Akka streams. We have our REST and our web application that acquires data from all of this, which is built out of Akka streams. What is Akka stream? Akka stream is an open source toolkit that helps build concurrent real-time application on a JVM. Basically, what it does is, if you have a multi-threaded application that you want to run, the work of creating the threads, managing it, and all of that is hidden under the hood. So the developer can just concentrate on building the business logic on top of it. It works on an actor-based model, but it also supports end-to-end streaming. So here is how the architecture looks like, or how Akka Streams works. We have HTTP requests coming in. Each request that comes in creates its own HTTP stream. We validate just the request and return back the response. At the same time, the event is materialized and it is sent to a long-lived enrichment stream. So this enrichment stream is the one that takes care of doing that geo enrichment, device detection, bot detection, intent, customer segment addition, and all of that, and it writes to a data sync as well. So this fan-in operation through a merge hub is something that is seamlessly provided by Akka Streams. So instead of writing a big piece of code, you just have, it is just a single line of code that helps do this fan-in operation. Akka Stream also provides multiple other things like fan out and so on, but you just have to, in this code, if you look at, it receives the request, materializes it, sends the response, and with just an single line as also to a particular stream that we want, it makes sure that the fan-in operation is possible. We have a framework called Cubes, which is built on top of the Akka Streams, and it's also open sourced. So in this framework, there's still one small problem, wherein in case the request is exorbitant, or if our data sync is not available for any reason, then you will start to lose messages. To avoid that, we use persistent buffer. The persistent buffer is built using Java Chronicle, and it is a part of this Cubes framework. By moving on from an Tomcat-based Spring application to the Akka-based Cubes framework, we were able to reduce the VM footprint by about 75%. And with the volume that we are growing, so from 18 billion to 25 to 40 billion, that the pace that we grow, I think the amount of savings that we get by this is enormous. Now that the data has all been collected, it has also been enriched. Now we need to make sure that it's available on a messaging layer, so any of the downstream products can use it. Each downstream can have their own framework in which they want to read the data and process it and use it for their use case. It should also be fail-proof. It should also support high throughput. So all this is what was needed from a messaging layer. And the solution that we used was Kafka. Kafka is fast because it uses the file system for storing and caching using sequential I/O. So, and there are a lot of tech stacks that are easily integratable with Kafka. So I don't have to go much in deep because it is now an widely used framework for messaging system. Some of the best practices that we use, I'll just share those. We set the AX, or the acknowledgement that we want to receive, as 0 or 1. So this tells whether the message that you sent did reach the broker, or was it written to the leader or not. We set it to 0 in cases where failure is acceptable, a minimal amount of failure is acceptable. The reason being, it is only for a period of time that it has to do a metadata refresh that this is going to happen, after which anyways it starts to back pressure or the message gets stored inside the persistent buffer. In case you want an optimal guarantee, we set the acknowledgement to 1. The linger period and the batch size helps determine how do you want to batch your messages. The messages that are batched is compressed together and then it is sent. So an optimal value helps determine what is the kind of throughput that you want. So for our data, you will have to determine an optimal size based on your message size, based on the number of partitions in the topic that you are going to write. And it also depends on the amount of RAM that you have on the VM that you are using. So this is one of the optimal sizes that we use for our use case. The compression type, again there are two things. You can either go for gzip compression or Z standard. If your Kafka version is less than 2.1, it is better to go with gzip. If it's greater than 2.1 z standard is even better. It adds a little bit of an increment on your CPU, but the throughput that you get out of it is much higher. Now that the data is put in Kafka, there are some use cases that can directly consume out of Kafka and do it. But there is also an out-of-the-box business insight that we have to provide, like the experimentation use case that I just said, to determine if there is a problem with any particular flow of a use case or something. So the data is processed. What we do is we do further normalization to convert it from an totally into an unstructured format to unstructured format. So to do that, we wanted a framework that would help, that would be fault tolerant, high throughput and scalable obviously, but it should also support the filter, transform operations. It should support multiple data formats in which we can write. It should also support partition data storage, and it should also support ML libraries. So the solution that we go for is Spark streaming. It uses an high level in thing called D streams, so which helps get a distinct data sets that we process as individual ones. Spark streaming or Spark as such is not very different because it is just built on top of the Spark API. I'll just go over a few learnings or few things that we did in our application. So we use the cryo serializer. We register all the new classes that we built into the cryo serializer, which actually helps get higher throughput. We have to determine an optimal value for min, max, and the initial executor, the executor memory, and the executor cores. How do we start on optimizing this is, so in our use case, we had 250 gigs of data to be read with a block size of 256 MB in our cluster. To do this, it needs 1024 tasks. How do we split it? We started off with an configuration of 256 executors, 4 core VMs, and 4 gigs of memory. You can start off with this, then start to tune it to reach to an optimal point at which you will get a higher throughput. The next thing is persisting and unpersisting. Everybody knows that in case a particular data, process data is going to be reused multiple times, or if the data is something that is, a driver run data, you generally go in for persisting it. So the computation is not carried out again and again. But once you start to unpersist the data, there were times at which the data wasn't cleared off from the memory. At those times, we use Spark session catalog.clear cache at logical intervals to make sure that the memory is cleared of that. The next thing is the max attempts on the Spark. Most of the failures that happen on the executors are either because it is not able to fetch a block, probably block is missing, or it is a case where it is not able to write to the local node, or one of those. All of these are kind of non-recoverable. So instead of using the default value of 4 where it tries and then starts to fail, we set it to 1 so it fails fast, moves on to a different executor to try it out, or you will be able to fix it and then rerun the job. The next thing is writing partition by. There are times where we would be tempted to do in a sequential format when we write a regular code. We would be tempted to filter the data from a process data set and then write. But what happens is each time you do a filter on a process data set and write, the processing is actually carried out by Spark again and again because it does a lazy execution. So instead, if you go in with an partition by, it actually does not have to do that processing multiple times, and it increases your throughput. It is generally, the next thing is dynamic allocation. It is generally a notion that dynamic allocation is not so good. But in our case, the load varies so much that during a peak period, the traffic that we get is twice the traffic that we get during a non-peak period. And hence we use dynamic allocation with the other set of configurations that I just mentioned above. And this helps use our clusters capability, optimally during all period of time. Then to stream data from Spark to any of the downstreams, we use Gimel. Is, in case you have, I don't know how many would have done it. In case you want to stream data from Spark, either to Druid or to Kafka, the amount of data that you have to write is at least a small function, or a little more than that. If you use Gimel API, it is like a data frame dot write or a data set dot write. All of that needs to, that it needs to understand which topic to write, what is, where are the broker details of it, the zookeeper details, or everything is actually hidden under the hood, and that makes it even more simple and elegant. Gimel is again something that's open source by PayPal. You can refer to gimel.io for further details. Some more learnings. Like I said, we persist what it is always better to persist repeatedly used or driver set data. We do sessionization, which is, something that's indispensable to understand the user's behavior over, in a complete session, and also compare multiple user session and so on. As a part of sessionization, it is general practice when we move on from our MapReduce environment to a Spark environment to store the events inside the, to store the in progress events into memory. But we changed that approach to store only the session details into memory and cross join against the events. So the amount of memory that we consume during sessionization is so less that it brought down our throughput, or the time that it takes for sessionization, to half. The last but not the least is getting comfortable with Spark UI. It provides all the information that you need to actually tune your application, starting with this, how it is split into tasks, each task into stages, the amount of storage that it uses at every point in time, how are your executors behaving, what is the kind of executor that it's choosing in case you have an heterogeneous cluster, and so on. Now that the data has been processed, it needs to be ingested into a layer which can actually accept the data that's coming at this pace, also do an aggregation faster, and provide response to your queries in sub-second latency. Only then the product managers or the analyst will be able to get a real-time insight of the data that has been collected and processed. So what was needed from an aggregation layer is massive real-time ingestion, sub-second query latencies, flexible data exploration. I would want to explore the data based on geo, device, customer type, the merchant he is coming from, what is the type of data that he is using, whether he is coming from an Comcast, 4G, 3G, whatever. And it also something that helps support business intelligence as well. So the solution that we use is Druid. Druid supports a Lambda architecture. So you can pump real-time massive data. It does aggregation real-time, and the queries are absolutely fast. Druid is good for our analytical use case in all sense. There are some learnings that we had as a part of our BI insights that we built on top of Druid. The first one is approx histogram and data sketches. I know everybody would be working on one of the aspects that the organizations have, which is site speed. So the percentile value is something that everybody would be looking out for. And we started off with approx histogram, played around it quite a bit. We also moved on to data sketches, played around it as well. But in both of these cases, we did not get accurate and consistent results. So, but that's probably because of the way our data is distributed. And it works on a specific algorithm in which it can actually guarantee you that approximate results. So what we did was we created our own buckets. We run the filter query to get the counts of the buckets, and we do the percentile computation on the client side. The next thing is there is no support to get the top n group by multiple dimensions. So there are multiple options to derive this. Either you can fire multiple filter queries, filter result, again based on that result filter get aggregated. But instead of that, doing a group by with order by column spec gives a better performance. There's the other use case that we had was a nested data model. So I have a JSON. It has a JSON internally inside it, and each element has its own set of metric. To query this, to store and query this data, Druid does not have a direct support because it is still flat. So there are again multiple options to achieve this, either flatten it and store it, or use multi-valued dimensions with metrics under it. But compared to all of that, we found that storing it as two different data models in two different data sources and doing a join on our client side seemed to give a better performance. Now that the data is all ingested, you can get results sub-second. What next? We've still not got value out of it. We want to make sure that the users are able to create any kind of a dashboard, run any kind of a query, and create visualization. So what was needed from a visualization layer? It has to integrate well with our aggregation layer. It should provide variety of graphs, bar, pie, line, whatever. It should also paint the graph at low latency, support multiple custom queries, and it should also support custom dashboard to be created, shared, and so on. We use Superset for the same. It integrates really well with Druid. There are no learnings because it is like you can just go in and any user will be able to understand what are all the data sources available, dimensions available, create a graph of their own. Now, stitching all of this together, we saw an acquisition layer does all of the collection, enrichment, making it available on messaging layer, which is Kafka. From there are different endpoints that are using it real time. We read the data out of Kafka, process it, and then send it to an aggregation layer, and we have a visualization layer on top of it. So dashboards can be created and real-time insights can be obtained. So now stitching this together, we have devices, we have the online transactions that are carried out, we have requests that's coming from our tenants and merchants like the Venmo, Zoom, and our merchant integrations. All of these requests come to our CDN edge nodes. They have to cross the firewall, reach out to our Scubes application or our Scubes REST application. We have the data coming from a constellation of microservices. So any request, any user interaction needs all the processing that's done in the backend by the services. So they also send data back to us. All of this data is written to Kafka, post-enrichment. A streaming process works on top of it, pumps it to Druid. Visualization is through Superset, and we also have an inbuilt analytics dashboard. From Kafka, the data is also read by a Spark batch application, and the results are written over to Hadoop. And the data is moved over to Teradata, and Tableau dashboards are built on top of it. We have Jupyter notebooks that can query Druid, Hadoop, Teradata, and it also has an integration with Tableau. So it becomes a seamless endpoint to interact with multiple data sources. For certain use cases, data is also fetched directly from Kafka, and it is ingested to Elastic. Because Kibana, Elastic provides a different kind of helps answer different set of use cases. So that's the one. This becomes our real-time pipeline, and this becomes our batch pipeline. Thank you.
So we are not done yet. Now let me do a deep dive on real-time use cases. So this is what happened. So now you saw the overall end-to-end analytics pipeline, like how we are solving the needs for our business analyst, our data scientist, machine learning, and AI engineers, right? So we are providing them the data which they need in a form which they want to consume. So that's all good. Now, with that, what's happening is like we started seeing a lot of use cases which different product teams and different applications teams are coming to us and saying, can you provide some of the other use case support from the platform perspective? So we started, let me show you like what those use cases are, right? So some of the product requirements are, what we just saw is basically doing a very generic insights, providing a platform where given any data which is flowing in, we can visualize and put that into superset and process that. But there are some cases where teams are asking and building their own pipelines for doing some of their own specific use cases. So is there any room for centralizing those things? Can we directly pump real-time insights or create some kind of alerts from the platform itself, right? The second one is another kind of use case. Can we classify users who are attempting a checkout but not completing it, and can we provide that as a stream to a different team? So we have this segmentation which power or which personalizes the user experience. Can we pump data in real time so that that can be enriched in real time, and any APIs which are calling them, they will have the latest and greatest data. Then there is this chat monitoring application which is using our platform, and they want to, whenever someone is coming and chatting with a customer agent, and they want to know the sentiments and what exactly they are asking, and provide some kind of a feedback to the agent in real time so that they can be much more engaging and much more helpful. And there were some use cases where, okay, we are collecting all this data in PayPal from all the products. And then there are some teams who are like, we want to see this data in some third-party system, maybe in Google Analytics or in Amplitude. Can we provide this data from our platform and push this data to this third-party solution? So we are not doing the integration on the client side, one for our internal system, one for Google Analytics, one for like other third parties, right? And can we handle some of the compliance requirements like GDPR in a central place? So these were the different requirements which we were getting, and we thought through these requirements, and what we understood by looking into this requirement is like every use case has some different needs. So first of all, the data stream which you saw earlier, we are ingesting 18 to 20 billion events per day, right? Which translates to somewhere around 200K to 500K events per second. And this volume of event, let's say if we put everything in Kafka and we don't provide some kind of intelligence there, every single use case will be consuming this heavy load. And it's not practical for all these use cases to just consume everything if they just need maybe like 1,000 events or just like a very small subsection of events, right? So like how we can solve that. The second thing is all these use cases, they need data in a different format. Like some use cases are happy if you just provide them filtered raw events directly in a different Kafka topic or a different sink. Some are like, can you do some kind of a sessionization based on correlation ID and give us some stream so we don't have to do that intelligence on our end. And some are like, okay, can you provide some more kind of intelligence where you are figuring out something based on all the parameters, all the data you have, and then giving us the right signals which we can use. And then on top of that, there were like some use cases where we write data to a Kafka and they are happy. Some use cases you need to call their API and then they can trigger their workflow, right? So the different use cases, different workflows. And the last one is basically these use cases needs to be onboarded very easily. And then if there is any update in these use cases, we can update in real time and make it available. So what we did is basically we created a two-part solution for these use cases. I'm going to show you the architecture and flow diagram of what we did, and maybe we can discuss this later. And so first step of this this workflow is basically we created a system based on again Kafka and Akka. Like we are a very heavy Akka and Sqube shop. And because we see the benefit of using these technologies in one place, we are trying to make it like everywhere use these technologies. And this is helping us handle the workload, the input pressure which is coming, and gives us very good throughput. So first phase is like we we have this main analytics cluster, which you saw in the messaging part of the analytics. All these messages are being written there, and platform is using some of these messages for doing some generic processing. And then for these business-specific use cases, what we did, we created an application. This application has like a two-part engine. Like one is a filter and transform engine, and what it does basically, it filters these Kafka messages. So it's receiving all these Kafka messages from this cluster, main cluster, and these messages now, based on some metadata, which is governed by the management tool, which you see in the bottom, it provides value. You can put some configurations there. You can put some criterias like what exactly you are looking for. So everyone has a different needs. Like based on the use cases which you saw, like they have different needs, and they don't care about all the data which we produce and which we generate for their use case. So can we just filter that data and provide them in some form, right? And then in some cases, there is some kind of a sessionization required. For that, we have a session storage, which we rely on sessionize the events. And then basically, we do different kind of a processing. So if we based on all these things, like there will be a lot of filtering happening, a lot of transformation happening. And since we are using Akka and actor-based model, we can create different actors, and they can do their job independently, right? So that's the power of using Scubes and Akka-based framework. And then what we do is we write these messages to different Kafka topics. So these Kafka topics can be in the same cluster as where our main analytics topic is, or they can be in a different Kafka cluster based on what the customer, what our application teams need. And the second part of this solution is basically we have now all these events are being returned to a separate Kafka topic. Now, some of these messages are directly read by the application team itself, but some of the teams, they expect some different kind of thing. Like, for example, those real-time business insights use cases. So what we do is we write them to we have a different piece, again, written in Akka and Scubes, which consumes these events from a Kafka topic and does some specialized visualization. And then users and scripts can come, and then they can read this data. The second class of use case is basically where we have some kind of APIs which are hitting, and then they want some data to be available to them. And for that, we have this another pluggable piece where we do some additional processing based on their use case, and we write the data to some kind of a data store which they can query in real time, and then they get the value out of it. And the last one is basically where we have to send data to the third external partners. And what we do is we basically read this data again, process, and dispatch to the third party. And the dispatcher has has inbuilt functionality for doing the retries and then making sure everything is being sent to the third party, right? So that's all basically the solution we have. Like, one is how we separate the different events into different stream based on different use cases we have, and all that filter and transform block which you saw, that is doing the heavy lifting, where we are using different actors for carrying out the fanning of the events and making it available for different use cases. And then based on the use cases, now they can be consumed and used, right? So that's all we have. And now time for question and answer.